Hello everyone, this is Raghavi, Assistant Professor from Department of Computer Science. Today we are going to see about the concept geometric transformation in digital image processing. First, let us see what is geometric transformation. Geometric transformations are widely used for image registration and the removal of geometric distortion. Common applications include construction of mosaics, geographical mapping, stereo and video. Next, let us see about spatial transformation of images. A spatial transformation of an image is a geometric transformation of the image coordinate system. It is often necessary to perform a spatial transformation to align images that were taken at different times or with different sensors. Next, to correct images for lens distortion. Next, to correct effects of camera orientation, and last, image morphing or other special effects. Next, let us see about the spatial transformation. In a spatial transformation, each point x, y of an image A is mapped to a point u, v in a new coordinate system, and the mathematical representation u equals to f1 of x, y. This represents the coordinates in the first image. Next, v equals to f2 of x, y. This represents the coordinates in the second image. That is mapping from x, y to u, v coordinates. A digital image array has an implicit grid that is mapped to discrete points in the new domain. Next, let us see about affine transformation. An affine transformation is any transformation that preserves collinearity. In general, an affine transformation is a composition of rotations, translations, magnifications and shears, and it is given in a mathematical representation as u equals to c11x plus c12y plus c13, v equals to c21x plus c22y plus c23, where c13 and c23 affect translations, c11 and c22 affect magnifications, and the combination affects rotation and shears. A shear in the x direction is produced by u equals to x plus 0.2y, v equals to y. This is the examples of a rotation and a shearing. The shearing and the rotation is given in a mathematical notation. U equals to x plus 0.2y, v equals to minus 0.3x plus y. The above image represents the image rotation in the x-axis, and the second image represents the image rotation as well as translation in both x and y-axis. A rotation is usually produced by specifying a theta value, which is represented in mathematical formula as u equals to x cos theta plus y sin theta, u equals to minus x sin theta plus y cos theta. Combination of transforms. Complex affine transforms can be constructed by a sequence of basic affine transforms. Transform combinations are most easily described in terms of matrix operations. To use matrix operation, we introduce homogeneous coordinates. These homogeneous coordinates helps us to enable all affine operations to be expressed as matrix multiplication. An equivalent expression using matrix notation is q equals to tp. Next, transform operations. The transformation matrices below can be used as a building blocks. They are translation, scaling and rotation. Translation is represented as scaling. Translation is we can perform a translation in both x and y direction, and the scaling we can also perform in x and y direction. Scaling is s1 and s2, and a rotation we can perform in a x direction and y direction. These are some of the examples of a translation of an image using scaling, rotation from a origin, performing a rotation and then translating an image with a rotation and translating the image back to its original position. Let us see an example in the MATLAB for image geometric rotations. Now let us see an example in a MATLAB. In this, first I am reading an image and displaying it using subplot. Next I am performing a rotation operation. For that I have specified the theta value in degrees as -30 for performing a rotation on the input image, and I am displaying it using subplot. Next I am doing a scaling. For that I am using a function imresize I am applying a scaling on the rotated image, so that I am passing a rotated image as an input to this scaling and displaying it using subplot, and finally I am performing a translation in the x-axis. Let us see the output. This is the output which we get. This is the original image. After performing the rotation operation, rotating it in -30 degree, we will get the second image as the resultant. And after performing the scaling operation, scaling is nothing but zooming in or zooming out the image. Next, the translation, we get the following output. We are translating the position of the image from its original position to a origin. Thank you for watching.